Hi, welcome back. This is differential equations. We're looking at 2.4 and we want to solve a particular kind of differential equation called the exact equation. And before we get too much into it, let's talk a little bit about integration when you have multiple variables. Okay, so how exactly does that work? Let's take a look. So we've dealt already with taking partial derivatives. Right? So let's say I have z equals xy squared plus y squared. Okay. The partial of z with respect to x would be what? Well, you pretend the y squared parts are constant and you just take the derivative with respect to x. So it would be 1 times y squared and then plus 0, because that y squared part would go away. Right? Okay, let's go now in the reverse direction. So if I wanted to integrate y squared with respect to x, what would I get? Well, one thing, you could totally just factor the y squared out of the integral because it's a constant. And then you would just be left with 1 dx. And then the integral of 1, of course, is x, and we would have y squared x, and then plus. So the way it used to be, we would have some sort of integration constant. Because if you took the derivative with respect to x, usually the only thing, if you had back in Calc 1, f of x equaled 3x plus 2, the derivative of that with respect to x, you would lose the 2 information, right? You would just get 3, and then if you integrated 3 dx, you would get kind of back to the original, but you wouldn't know that you started with a 2, right? Here, rather than potentially just eliminating a constant, what you potentially eliminated was a function of y. So we have the xy squared, which is like this part here, but we're not going to put a plus c because we potentially have eliminated a function of y, and in this case, we definitely have it. So we're going to put g of y instead of just putting plus c. So if you integrate with respect to x, and you're dealing with a multivariable function, rather than going plus c, you just go plus some function of the other variable. Okay. So we have then, rewriting it with x in front, xy squared plus g of y. And again, you could see kind of this relationship. Yeah, we were able to figure out the first part. We could recover the xy squared, but then that y squared is kind of lost in space, right? Okay, so let's take a look at the same thing and now do it with the y. So integrate with respect to y after we do a partial with respect to y. So here I have the partial of z with respect to y. Okay. So in this case, I'll have a 2yx and then plus 2y. Okay, so I'm going to go ahead and integrate that with respect to y and try to get back to where I started. 2yx, or 2xy if you'd rather. I'm just going to go with 2yx. And I want to integrate with respect to y. Okay. So the first term, I could go, I'll get 2y squared over 2x. The x is just a constant in this setting. Then plus 2y squared over 2, and then plus a constant, right? And so in this case, because I originally, because I'm recovering in the y direction, I could have potentially annihilated something in terms of x, right? So if I had z equals, and I don't have that case here, but if I had z equals xy squared plus y squared plus x cubed, and I took the partial of z with respect to x, you would, with respect to y, excuse me, you wouldn't see that x cubed anymore, right? You would just get the 2xy plus 2y. And so what we do, and again, instead of a plus c, we're going to have to put some function of x into that space. Okay, so that's kind of some of the weirdness we're going to be encountering here. in our exploration. It's not a big deal if you kind of already took multivariable, but for those of you who haven't, hopefully it's not too big of a pill to swallow. Anyways, just very simply doing some integrals with respect. Oh, wait a second. Okay, so let's talk about okay. So hopefully that won't be too big of an issue. Let's talk about the differential of a function. Okay, so excuse me, section 1 integration. Let's talk about section 2, the differential. Hopefully I'm not off topic now. Somebody just came into my office hour, so I had to pause the video there. Okay, differential of a function. In particular now we're looking at a function of 2 variables. So before in Calc 1 differential, how did that work? We had something like y equals f of x, and then you took the derivative dy with respect to dx equals f prime of x, right? But we could always rewrite this as dy equals f prime of x dx. Okay. This form is called the differential form, and probably geometrically that's where we can kind of connect it to where you are going to be now. So back here, the idea was you're kind of approximating a change in y via the derivative. Okay, so there's going to be 2 changes: the change associated with this tangent line, which I'm trying to attach to the curve here, but there's also the actual change associated with the functions. So this is not the actual change. The actual change in y would be the difference between the y height after some change in x. So we'll say f of x plus h minus f of x, right? That would be the actual change in height. The dy equals f prime of x dx is the change in the tangent line. So there's like this little amount, that would be your dy. Okay, they have the same idea now with multiple variables. We'll have y equals f of x comma y. It's just to describe the derivative with multiple variables, you kind of need a change in x and a change in y. And geometrically, what that is kind of a tangent plane as opposed to a tangent line. So what will happen is there will be a change in the x direction like this. And this is like a 3-dimensional kind of picture here that I'm drawing. This is the x-axis, this is the y-axis, and then this is the z-axis. So there'll be a bit of a change in the x direction. There'll be some sort of bit of change in the y direction. And it's those 2 pieces of change which result in the change in the y direction, change in the z direction, rather. Okay, so it's a sum. So you'll have, let's kind of block this off here. That's my change in x. But then there's also going to be a change in y kind of added on top of it. So you can see that triangle there, that triangular region here. I'm going to plop that on top of my change in x. And that should give us the change in z. Okay, so this height here is my change in z. And yeah, so it's the change in y plus the change in x that gives you the change in z. And so you're going to see a sum in your differential. So we can take the derivative of this with maybe some other variable. Let's call it t. So rather than calling it y, we don't want to call it y, right? Let's call it z. I'm trying to find my little marker set here. Let's call this z. And then we're kind of taking the derivative of that z with respect to some other variable t. And so there'll be kind of 2 parts. There's the change in the x direction times this dx over dt, plus the change in the y direction, dy times dy over dt. And if you multiply both sides by dt, then you get kind of the differential form, but the multivariable version of it. So you get dz equals the partial of f with respect to x times dx plus the partial of f with respect to y times dy. Okay, so if nothing else, hopefully you can kind of attach your learning at this point to this idea that what we're dealing with here is basically the differential form of the derivative in 3 dimensions. Okay. If on top of everything else it turns out that this z equals f of x y is equal to some constant, then we could rewrite this differential form. So suppose then that f of xy is equal to some constant, then we could rewrite our differential form equal to 0. Okay? So dx plus the partial of f with respect to y, dy, it would be equal to 0. Okay, it's this thing that is going to be our exact equation. And so what we're going to be after is this function f of xy, and we're trying to recover that from the partial derivatives. Okay, so section 2 now, this thing, I guess it's section 3 now, this thing we're going to be calling the exact equation. Instead of writing the partial with respect to x, I'm going to put a big M of xy. Okay, so it'll be M of xy dx plus, and then instead of writing the partial with respect to y, I'm going to write this function of x and y, n of x and y. So n of x comma y dy equals 0. Okay. For not all of these kinds of equations have this this function which would result in this expression if you did the differential. So to make sure that it actually has kind of a solution, there is some conditions. So let's make note of that. The conditions for solving these exact equations, we need m of x comma y and this n of x comma y. We need these things to be continuous with first partial derivatives and I need the partial of m with respect to y to equal the partial of n with respect to x. Okay, if you took Calc 3, you kind of already dealt with this. It comes up in the fundamental theorem for line integrals. It's the criteria for the mixed partials to be equal. Because, I mean, if you think about it, this m of xy is a partial with respect to x, and then you're checking the partial with respect to y. So it's really the mixed partial being equal to the other mixed partial that is the condition for kind of finding the anti-differential. Okay. Okay, so anyways, let's take a look at kind of the method. The method I use is a bit different than what they kind of show in the book. I think mine's a little bit more direct and encompasses everything they want. So let's take a look here. They go through it very abstractly, and then they kind of have a lot of writing. When I do it, it's all just, math. I don't worry about writing anything out, but let's take a look. So solving these things. So we basically, what do we need to do? We need to find a function f of x comma y such that when we take the partial of it with respect to x, we get this mx thing, this m of xy, And when we take the partial of it with respect to y, we get this n of x comma y, right? So what you're going to be able to do is to basically back engineer a kind of image of the function, and then take its partial and align it with the appropriate partials. So the picture I'll kind of draw it here out. So you have m dx plus n dy, and what's there's some potential function up here in space f of xy, and to get m, you're taking the partial of f with respect to x. To get n, you're taking the partial of f with respect to y. So, noting this picture leads us to the following. If you take the partial with respect to x of the integral of m with respect to x, well, wait a second, the partial with respect to y of so if you took the integral of m with respect to x, what's going to happen is you'll end up back here, right? That would be the integral of m with respect to x. So once you're up here, then you could take the derivative with respect to y, and you should get n. This thing right here that is created should equal n. That is basically the equation you're going to use to solve all these problems. You could also say, going in the other direction, just take the partial with respect to x of the integral of n with respect to y and set that equal to big M. Either will work. Okay, so I mean, that's really it in a nutshell. The book kind of, I think, beats it to death, but yeah, you're just looking for this function. They give you m and n. So basically, you just integrate, then partial it, then equate. So let me show you. Okay, so let's take a look at example 1. So we have 2xy dx plus x squared minus 1 dy equals 0. You still have to check it before you do anything else, because not all of these are going to be exact. And you'll see that in your homework. When that happens, you just write none or not. They want you to write not in capital letters. Okay, so anyways, so this thing right here is your m. This thing right here is your n. So you need to take the partial of m with respect to y, and that will equal 2x. And make sure that's the same as your partial of n with respect to x. And of course, that's 2x as well, so we're good there. Okay? So once that's checked off, then you just take the partial with respect to y of the integral of m, which is 2xy, and put a dx in there. So this integral will recover you back to f of xy, but it's not going to be complete, right? There's going to be this, because you're doing an integral of a multivariable function with respect to x, you're going to have this plus g of y term, which is unknown. Okay, but by equating it, by taking the partial and then equating it to whatever n is, you'll be able to solve for that unknown function. Okay, so let's try that. So first integrate 2xy dx. So that will equal 2x squared over 2y. Let's just write x squared y. And then plus the function, some function that was potentially destroyed in the differentiation process, g of y, right? We'll set that equal to x squared minus 1. That is your answer. Believe it or not, this thing right here is pretty much your answer. This is what we're going to be setting f of xy equal to. The only problem with that answer, like I said, is that g of y function. It could equal something. Okay, so let's do the partial of that. The partial with respect to y is going to be x squared plus g of y prime. On the other side, I have x squared minus 1. Okay. The x squares will cancel, and you just have g prime of y equals -1. And then you just take the integral on both sides with respect to y. And that should allow you to solve for this unknown function, g prime of y. So you get g of y equals -y plus some constant if you want, but we don't need that part. Just the -y part is what we need for our answer. Okay, so our answer is going to be, you kind of just use this, x squared y minus y, and then that'll equal some constant. Okay? So let's see what the book has as their answer. Do they get the same thing? Yeah, x squared y minus y equals c. If you need the explicit solution, you could solve for y, but there it is. Okay. Okay, let's do another example then from the book. So example 2. I have e to the 2y minus y cosine of xy dx plus 2x e to the 2y minus x cosine of xy plus 2y dy equals 0. Again, first things first, you have to check to make sure that our criteria are fulfilled. So you need the partial of m with respect to y. This thing here is your m. This thing here is your y, or sorry, your n. Okay, so the partial of m with respect to y is going to be e to the 2y times 2. And then I'm going to have to do a product rule on this part. So minus, I'm going to leave y alone and take the derivative of cosine xy. So that'll be the negative sign. Let's make that positive then. So sine xy. And then the chain rule says the derivative, we have to take the derivative of the guts there, the xy. The derivative of xy with respect to y is just x. Okay, so that will be 2e to the 2y plus xy sine of xy. Okay, let's do the partial of n with respect to x. Okay, so the first term there with respect to x is just 2e to the 2y. Then I'm looking at, again, I'm going to have to do a product rule on this next part. So minus the derivative of cosine xy is going to be negative sign, so I'll have minus x, but then it'll be plus, and then sine of xy, and then the chain rule, the derivative of xy with respect to x will be y, and then the derivative of 2y with respect to x will just be 0, so we get 2e to the 2y plus xy sine of xy, and so the mixed partials are equal, and you're good to start your next step. Okay, so now we go to the partial with respect to y of the integral of m with respect to x. So e to the 2y minus y cosine xy with respect to x, and that should equal n. Okay, so let's go at it. So first, the integral of this thing with respect to x. The first term, e to the 2y, would just be constant. So it's x e to the 2y. And then minus the y part is just constant. And then the integral of cosine of xy, you would need probably a u sub. Okay, so over here to the top right, I'm doing the integral. I pulled out the negative y, and I have the integral of cosine of xy dx. So you can do a u sub, let u equal xy, and then du will equal, and the x is the variable, so du would be y dx, and then dx will equal du all over y, and so I'll have negative y integral of the cosine of u times du all over y. You can factor out the y, because that's constant, so you get negative integral of cosine u du. Integral of cosine is just sine, so negative sine of u plus a constant, and then that would be back subbing negative sine of xy. So, and no, I didn't lose my y in front. Okay, so then it's, yeah, the negative is correct. Yeah, so minus sine of xy, plus the sort of unknown part, this g of y thing. And then that'll equal 2x e to the 2y minus x cosine of xy plus 2y. Okay, so again, this is your solution. Okay, we just need to figure out what g of y is. So take the partial with respect to y. I get x e to the 2y times 2 minus, this will become cosine of xy, and then times the chain rule. This chain rule says the derivative of xy with respect to y will just be x, and then plus g prime of y, and then this equals 2x e to the 2y minus x cosine of xy plus 2y. So this and this cancels, this and this cancels. G prime of y is 2y. Okay, almost done. Integrate both sides, and you get g of y equals 2y squared over 2, so just y squared. And finally, then your solution, x e to the 2y minus sine xy plus y squared equals some constant. Okay, so let's make sure that's what they got. Yep. They like to put the constant on the other side instead of equal to 0. That's fine. Okie dokie. Let's look at example 3. So we have an initial value problem, which looks like it's kind of scrambled, a scrambled mess at this point. So I have dy all over dx equals xy squared minus cosine x sine x all over y times 1 minus x squared, and they give you an initial value in this problem, so you can solve for your constant c. Okay, so let's move that over a little bit. All right, so I'm going to kind of cross multiply first off. So I get y times 1 minus x squared dy. On the other side, I get xy squared minus cosine x sine x dx. I'm going to move the right side to the left side, and I get y times 1 minus x squared dy equal minus, okay, minus xy squared minus cosine x sine x dx, and then it'll equal 0. Let's go ahead and distribute stuff. It'll just make it easier when we take derivatives. Less probability of mistakes, at least for me. I like to do this. Okay. Anyways, what I'm doing is just getting it into kind of the standard form of an exact equation, and now it's easier to identify the m and the n. So anyways, the partial of m with respect to y is going to be 1 minus x squared. The partial of n with respect to x is negative y squared. What the heck am I doing wrong? Oh, these are reversed. Ugh. Sorry. So the dy, the m goes with the dy. I apologize. So this is my n, and this is my m. Okay. So anyways, the partial then of m with respect to y, otherwise it wasn't going to work, was it? Is going to be negative, I guess what do we have? Negative y squared, whoops, with respect to y, so I think, sorry, negative 2xy, and then the cosine x sine x is just 0. Then the partial of n with respect to x is going to be, the y will be 0, and then minus 2, so that works. So those are equal, and we're good to go. Then I'm going to do my partial of m with respect to, so we need the whole integral thing, right? We need first the integral of m, so negative xy squared plus cosine x sine x dx, and then take the partial of that with respect to y and set that equal to n. Okay, there we go. So integrating with respect to x gives me negative x squared y squared all over 2. Then this thing, there's a couple ways you could pull this off. You could do a u sub. There's probably some weird identities you can use. I'm going to do a u sub. Let u equal sine x, and then du will be cosine x dx. So that part of the integral there will become u times cosine x dx, which is u du. And then if you integrate that, that'll just give you the u squared over 2 plus your constant. Back subbing, then you get plus sine squared x all over 2 plus this g of y thing that we always worry about, and then that's y minus x squared over y. Take the partial with respect to y, so you get negative x squared times 2y all over 2, so negative 2x squared y. Is that right? Oh, was the 2's cancel, sorry. So just negative x squared y, and then plus 0 for that sine squared x, because that doesn't have any y stuff in it, and then plus g prime of y equals y minus x squared y. The x squared y's cancel, and you get g prime of y is y. So y squared over 2 for g of y. Y squared over 2. And then we can kind of get our solution, or a peek at it. So we got negative x squared y squared over 2 plus sine squared x over 2 plus y squared over 2 equals a constant. Then we use the initial condition, which was y of 0 is 2, in order to solve for the constant. So we get negative x squared y squared, but we need to plug in 0 and 2. Okay, so the x is the 0, and then the y is the 2, if that's not clear. So plugging in 0 in the first term will just be 0. Then the second term, sine of 0 squared, sine of 0 is 0, so that whole thing will just be 0. And then finally, plugging in y is 2, so y squared is 4, all over 2 is 2, equals c. So our answer should be x squared y squared all over 2 plus sine squared x all over 2 plus y squared all over 2 equals 2. There's probably nicer ways to write it, but let's just make sure that's what they got. And sort of, right? Okay, so they got, first let me get rid of the 2's, so I just need to make sure I got the same answer, right? Plus sine squared x plus y squared equals 4. They found c was 3, so their answer is y squared times 1 minus x squared minus cosine squared x is equal to 3 somehow. So their answer is y squared minus x squared y squared minus cosine squared x is 3. So how is that my answer? And I claim it is. If you take my answer and go like this, so negative x squared y squared plus sine squared x plus y squared equals 3 plus 1, because 3 plus 1 is 4, and then move the 1 to the other side, you get negative x squared y squared minus 1 plus sine squared x plus y squared equals 3. Then you could factor out a negative from the negative 1 plus y squared, and you get negative 1 minus sine squared x plus y squared equals 3. And then the Pythagorean theorem, the conjugate, the Pythagorean, what do they call those? Anyways, that thing is going to be cosine squared, right? Because we know cosine squared plus sine squared is 1. So this would be minus cosine squared x plus y squared equals 3. And certainly my answer is the same, so no big deal. Okie dokie. So let me just do one, probably from the homework. But it seems like some of the beginning homeworks are kind of easy. So let me just try number 3 and see how that goes, if it allows me to look at it. So we have 2xy squared minus 5 dx plus 2x squared y plus 6 dy equaling 0. Right, so first, make sure the partials are equal. So partial of m with respect to y is 4xy, and the partial of n with respect to x is 4xy, so that works. Then we're going to do our method. Okay. Right, so integrating that thing, we're going to get, with respect to x, 2x squared over 2y squared, which would just be x squared y squared, minus 5x, and then plus our unknown function of y, equals 2x squared y plus 6. This one may have been just... anyways, partial then with respect to y, so you get 2x squared y minus 0 plus g prime of y equals 2x squared y plus 6. G prime of y will equal 6, so g of y equals 6y, and then we should be able to write out our answer, right? So it's this thing, x squared y squared minus 5x plus 6y equals our constant. Every once in a while, just as a warning here, this g prime of y will equal 0. And sorry, I couldn't find an example. That's the example I was kind of hoping to get. But in that case, when you integrate both sides, you're just going to get g of y is equal to some constant. And that constant you could just put on the right side with this constant c. I was hoping to find one of those, but of course, I was unable to. And of course, they won't give you one of those examples in the book. So anyways, sometimes, even if it turns out that the thing isn't exact, in other words, when you're checking if these mixed partials are equal, this partial of m with respect to y and the partial of n with respect to x, sometimes they won't be equal, but you could still fix the issue. Okay, I'm just looking for what number I'm on number 5. Okay. So to fix the issue, what you're going to do is use an integrating factor, and a little similar to what we did before with our first order linear differential equations. It's kind of like that idea, but the integrating factor is different. Okay, so you do this when the partial of m with respect to y does not equal the partial of n with respect to x. When you do this, then we may be able to save it. And this does not equal, we may be able to save the situation by constructing a function mu so that if we were to multiply the original exact equation by it, the partial of m times mu with respect to y will equal the partial of m times mu, n times mu with respect to x. Okay. Okay. It's from this relationship that I'm actually able to kind of figure out what that integrating factor mu should be. So if I were to kind of expand this thing here, notice that you need the product rules, right? So it'll be the partial of m with respect to y times mu. So you leave mu alone, take the partial with respect to y, plus then take the partial of mu with respect to y and leave m alone. And on the other side, that should equal the partial of n with respect to x times mu. So you get mu times nx, plus then you leave n alone, take the partial of mu with respect to x. So you get mu with respect to x times n, where again this notation m sub y, that's basically just the partial of m with respect to y. Mu sub y is the partial of mu with respect to y, etc. Okay, in case you've not seen that notation before. All right, so if you have that the mu of y is equal to 0, then you can kind of solve this equation for the integrating factor. So in this case, mu my plus 0, right, because mu of y is 0, so 0 times m is just going to be 0. Mu times my would equal mu times nx plus mu with respect to x times n. Then you could, you want to solve for mu, right? So you could bring this over to the other side or vice versa, and let's write the mu x on one side, put the other stuff on the other. So mu my minus mu nx, and then factor out the mu, and you get my minus nx. And then you could integrate both sides with respect to x. I want to move the n over first. Okay, so I have, so I'm basically separating, right? So my minus nx all over n. I'm going to move the mu over too. So mu with respect to x, 1 all over mu equals my minus nx all over n. And then integrate both sides with respect to x. On the left here, you'll get the ln, the absolute value of mu. On the right, you'll get just leave it as the integral of this stuff with respect to x. And then exponentiate both sides. Do a little bit of hand waving, and this thing is your integrating factor, believe it or not. But in order for you to pick this, it has to be that mu of y equals 0. Okay? Or if you find that mu of x equals 0, then you use the integrating factor e to the integral of nx minus my all over m dy. Okay? Which I found just by kind of doing the same process as above. Okay. So anyways, let's look at the example they have for us. Example 4. Let's see what happens. So we have xy dx plus 2x squared plus 3y squared minus 20 dy equals 0. You may need to play around with it a bit, okay? Because of this condition that you need to find a mu of x that equals 0, which would imply that this thing is completely dependent on y. Okay, so this must be some sort of function of y for that to work. So this must be mu must be a function of y, or we need that mu sub y is equal to 0, which in that case mu must be a function of x. Okay, so what we're going to do is look at just these exponents, the inside of the integrals. And so we need either that first one to be completely a function of x, in which case when you took the partial with respect to y it would equal 0, or we need the second one to be completely a function of y. Because in that case, if you took the partial with respect to x, that would be 0. So we investigate those things. I need mx and I need my, or rather I need my and nx and for either case. So my is going to be x, and then nx is going to be 4x. So then I check out the two terms, my minus nx, all over, I think it was n. Okay, so in this case, it's going to be x minus 4x all over n, which is 2x squared plus 3y squared minus 20. Simplifying it, negative 3x all over 2x squared plus 3y squared minus 20. This is bad, okay? This is what we don't want, and it's because it's a multivariable expression, okay? This won't work. Because if you took the derivative, and in this case, we would want the derivative with respect to y to equal 0, it just wouldn't. It wouldn't equal 0 because you got that y in the denominator. Okay. Let's look at the other form then, the nx minus my. Minus my all over m. Let's make sure that's right. Nx minus my, yeah. Okay, so in this case, it's 4x minus x all over xy. That'll equal 3x all over xy, which will equal 3 over y. This will work for us. This is exactly what we want. Will work for us. Because if you took the partial of this thing with respect to x, it's going to equal 0 because there's no x term in it. Okay, so our integrating factor then is going to be e to the integral of that 3 over y. Okay, so hence mu is equal to e to the integral of 3 over y, and we're going to integrate with respect to y up there. So make sure I got that right, yeah. So note this first mu has dx right here, and then the second mu has a dy right here. Okay, so anyways, what will you have then? E to the 3 ln y. As usual, when you're dealing with this, you could kind of avoid the absolute values. That's really dependent on which interval you're in. We're not given an interval here, though. I'm just going to go kind of by the seat of my pants and just presume I don't need the absolute value. Okay, so I'll have e to the ln of y cubed, doing a power rule on this, and that'll be y cubed. Okay, then I'm going to multiply the original differential equation, the exact equation up there, by y cubed. Okay, and I'll distribute it in. I'm going to refer to the original problem here. So I'm going to end up with xy to the 4th dx plus 2x squared y cubed plus 3y to the 5th minus 20y cubed dy equals 0. And now this thing should be exact. If you go and check it, then hopefully you'll see that. That'd be 4xy cubed partial of m with respect to n, with respect to x, then would be 4xy cubed, and the rest will be 0. So see, it works now, and now you can use the methods from earlier in the section to solve because it's exact now. All right, so here we go. I'm going to go partial with respect to y of the integral of m. Right, and that should end up equaling this 2x squared y cubed plus 3y to the 5th minus 20y cubed. Okay, so here we go. I got the partial of, with respect to x, that should be x squared y to the 4th all over 2 plus this weird function g of y, which may have been annihilated. On the other side, 2x squared y cubed plus 3y to the 5th minus 20y cubed. Take the partial with respect to y on the left, so I get 4x squared y cubed over 2, which should be 2x squared y cubed, plus the derivative of g of y with respect to y. On the right-hand side, then I have the 2x squared y cubed plus 3y to the 5th minus 20y cubed. These guys will cancel, and then you just find the antiderivative of 3y to the 5th and negative 20y cubed. Okay. So g of y will equal 3y to the 6 over 6, so y to the 6 all over 2 minus 20y to the 4th over 4, so 5y to the 4th. And so our solution, borrowing this thing, is going to be x squared, trying to get the black back, x squared y to the 4th all over 2 plus y to the 6th all over 2 minus 5y to the 4th, and that will equal your integration constant, okay? Which is exactly what they got. Okay, so there's like a couple of those in the homework towards the end for you. In the beginning, they kind of just walk you through it, and hopefully it won't be too difficult. Anyways, I think that will do it for this section, and we'll leave it there. As usual, thank you for watching, and I will see you next time. Whoops, I forgot the quiz. All right, so let's do one more problem. We'll make that the video quiz for the day. I swear sometimes. Let's just do number 1, or actually let's do this number 5. Okay, hopefully this will be one of those ones that I was talking about earlier. This y squared sine x. This is the video quiz problem. Video quiz. Let me mark down my notes. This is the video quiz. So it's problem 5 from my WebAssign. So 5th plus y squared sine x dx. I'm going to have to pull that other term to the left side if you're reading it over there in WebEx or WebAssign. Just to read that. Okay, so it's equals, but I'm going to move it to the other side and distribute the negative. Okay, so plus negative 5xy to the 4th minus 2y cosine x dy, and that'll equal 0. Okay, so first I need to make sure that the partials work. So the partial of m with respect to y is going to be negative 5y to the 4th plus 2y sine x. Partial of n with respect to x then will be negative 5y to the 4th, and then plus 2y sine x. Okay, so that works. Then I'm going to my process, the partial with respect to y of the integral of x minus y to the 5th plus y squared sine x with respect to x here. That should equal negative 5xy to the 4th minus 2y cosine x. Okay, So let's go ahead and integrate. That will be x squared over 2 minus xy to the 5th minus y squared cosine x plus this unknown. Oops, just g of y. And that'll equal negative 5xy to the 4th minus 2y cosine x. Get your partial with respect to y. The first term is 0. The second term, negative 5xy to the 4th. The third term, negative 2y cosine x. The this fourth guy, g prime of y, and that equals negative 5xy to the 4th minus 2y cosine x. Okay, so this is one of the ones where pretty much everything cancels and you just get g prime of y is 0. That just means you're going to have a constant for g of y. G of y is some constant c. And in those cases, you could just put the c on the other side. So where's our solution? This thing is the solution. So you can just write x squared over 2 minus xy to the 5th minus y squared cosine x plus c equals some other constant, but just put all the constants on the right so you have equals c for your final answer. Okay, hopefully that makes some sense in that process, although it's much different than what they present in the book. It's the same thing, it's just, I think, hopefully mine's a little bit more streamlined. And yeah, okay, so anyways, that was the video quiz. Just copy it down. And okay, let's stop the video there then. And as usual, thank you for watching, and we'll see you next time.